Hello and welcome to this talk. My name is Artem, and I will tell you about the work I've done with Lahav on taming x86 persistency. So persistence is a property referring to the characteristic of memory state that outlives the computation that creates it, regardless of whether this computation ends successfully or crashes due to a hardware failure, operating systems failure, or a power outage. And in memory hierarchy, CPU registers, a hierarchy of caches and random access memory, are volatile. But that is also where programs and data basically live as long as the computation goes on, but not after a crash, because the state of volatile memory gets lost when that happens. To make sure data outlives crashes, programs can transfer data to disk storage, which is non-volatile. So that is where data will persist. And for the last decade or so, researchers had been anticipating the arrival of non-volatile RAM. And as of 2019, it is available commercially, and we can all buy Intel Optane chips. This non-volatile RAM has desirable economic and performance characteristics, so it is expected to replace volatile RAM either partially or entirely. In both cases, persistence is going to be more easily available to programs. Something to keep in mind, though, is that modern CPUs, as they issue writes, do not write to memory directly. Instead, written values get buffered in CPU caches that are volatile. So something that can happen is that a CPU issues a write, and then a crash happens, and the value gets lost before it reaches a non-volatile memory. Something else that can happen is that a CPU issues two writes in one order, but they reach non-volatile memory in the opposite order. So in order to make sure that programs persist data correctly, it is important to understand the exact interactions between writes and the non-volatile memory. Fortunately, members of the POPL community have proposed a formal persistency semantics for x86. They discussed it with Intel engineers and came up with an extension to the total store order memory consistency model of x86 that has an extra persistence buffer. And in those terms, they explained how writes can persist non-deterministically and out of order, and how one can use persist instructions to enforce a desirable order of persistence. Nevertheless, there is still a gap between the common understanding of persistency and the POPL 20 model. And this gap comes from a decade worth of research from algorithms and system communities, where commonly special persist instructions such as CO flush are described as actually flushing a cache line, and in this way ensuring that writes reach non-volatile memory. Whereas the POPL 20 model would say that instructions like CO flush only restrict the order of persistence without ever flushing writes into memory. In fact, it's possible to have executions under the POPL 20 model where no writes are ever flushed into the non-volatile memory. So we identify the gap in understanding here and raise a question: does all the prior work need to be revisited in order to make sure that it executes correctly under the POPL 20 semantics? And more broadly, what is the connection between these two approaches, where persist instructions are eager and kind of flush in a more synchronous way, and this other approach where persist instructions are asynchronous and only enforce the order of writes reaching non-volatile memory? The gap in understanding is actually wider. The POPL 20 model works with weak consistency, but weak consistency only, whereas programmers commonly like to work with a stronger consistency model, sequential consistency. And that is even though hardware is usually weakly consistent. It is made possible by compilers and compilation schemes that that can instrument programs and insert memory fences in the right places, and in this way enforce sequential consistency. Also, programmers can write data race-free programs, and for those there is a guarantee that they do not observe the effects of weak consistency and have only sequentially consistent behavior. But that is only true in the memory consistency world. So since sequential consistency is so important, we raise a question: how do we provide an illusion of sequential consistency under persistency models for x86? There we would start with a natural question of what does it even look like to have this illusion of sequential consistency. So this is what this work is about. We raise a question of what is the connection between this prior work that commonly and usually informally assumes a more eager and synchronous flashing behavior of persist instructions, and whether that needs to be revisited in the light of the POPL 20 semantics, to which we answer no. We approach this by proposing our own model for x86 persistency, PTSOSYN, that has this eager and synchronous behavior of persist instructions. And we prove that this model is actually equivalent to the POPL 20 model. We also raise a question of providing an illusion of sequential consistency under persistency models for x86. And to address that, we formalize what persistent sequential consistency means as our PTSOSYN model without store buffers, which is actually not trivial to do, since, for instance, removing store buffers from POPL 20 model results in something that is too strong for the purpose. We also prove a theorem that gives sequential consistency semantics to data race-free programs and propose a simple compilation scheme. So let's take a look at a toy example of a pre-allocated sequential stack. So here we have an array of fixed size and a variable top that points to the last element pushed into the data structure. And in fact, maybe I want an invariant preserved about the top that says that top never points to question marks. It never points to garbage that can be in this array. Well, let's see what happens if I try to push 23 into this data structure. So I go ahead and read the value of the top and understand that what I need to do is to write 23 into A4 and also to increment top afterwards. So for now, these two writes are in volatile domain. And as we already know, these writes can persist non-deterministically and out of order. So the write to the top can go first to non-volatile memory. And then, well, let's say a crash happens. And we inspect non-volatile memory after the crash as we recover from it. And we see that top is now 4, and it points to question marks. So the invariant is violated. Well, if I want this invariant to be preserved, I will insert an explicit persist instruction, CO flush, after writing to A4. And this CO flush will make sure that the invariant is preserved. However, the specific way it achieves that depends on the particular model of persistence. Well, let's take a look at our model, PTSOSYN. Here I have a picture that is best read from bottom to the top. And the idea here is that cores, as they issue instructions, they put them in store buffers if those instructions have to do with writing data to memory. So every core has its own store buffer, and once instructions propagate from those store buffers, they go into persistence buffers. In principle, there can be just one large persistence buffer with some tricky ordering constraints. But in our model, we would choose to have one persistence buffer for every memory location. And such persistence buffer is a perfect FIFO queue. Such representation accurately captures what ordering constraints there are. So per location, these persist events are happening in order, whereas events to different locations are not ordered at this level. So once events leave persistence buffers, they persist and go into non-volatile memory. Something else I want to add is that is how reading works. So if we, for instance, read the value of top in the push method, we will first look for it in the store buffers, and then we will look for it in the persistence buffers, and only then we will go to non-volatile memory. So returning to the toy stack example, which is sequential. So we will have only one core, one thread of execution, and accordingly one store buffer. Let's say that we already issued the two writes that are in the push method. So the write to A4 and the write to the top are in the store buffer now. So writes propagate in order from the store buffer. And for that reason, A4 will go out of the store buffer first. And then it is possible that the write to the top also propagates. These two writes are in different per location persistence buffers, and they are not related to each other in any way. So both, well, persisting either of them is possible at this stage. And that is how the write to the top can go out of the persistence buffer first and invalidate the invariant, possibly. Well, let's see what happens once we add the CO flush. When CO flush gets issued, it also adds an entry into a store buffer. So that's why we have FL of A4 in it right now. And so the events will propagate from the store buffer in order like before. So A4 goes first. And now the new thing is that it is not possible to propagate the flush of A4 until the persistence buffer of A4 is empty. So the only possible transition now is to persist the write to A4, which is what we do. And only then we can propagate this flush entry from the store buffer, as well as the write to the top. And in this way, we enforce the property that the write to the top reaches non-volatile memory later and preserve the invariant. The way this will look like under the POPL 20 model is somewhat different because the buffers technically are different and have different ordering constraints. And also the persistence buffer is a large persistence buffer that doesn't behave like a queue. But let's take a look step by step how things will work. So like before, we will have CO flush already issued and with an entry in the store buffer. So there is a FL of A4 there. And let's say that the write to A4 propagates from the store buffer first. Now, as we propagate the FL entry, it will add a new special entry into the persistence buffer, per, which will serve a purpose. So let's say that now the write to the top propagates, and here we get to the purpose of this per entry. In the POPL 20 model, this per entry enforces more constraints on how events propagate from the persistence buffer. It is only possible to do this now in order. Only A4 will go first, and only then it will be possible to persist the write to the top. However, curiously, there's actually no requirement to flush persistence buffer at all. But if it does happen, then A4 goes first, and then the write to the top. So overall, I've showed you two ways in which the CO flush instruction can ensure that the invariant is preserved. So there was this more synchronous, more eager flushing approach, and this asynchronous approach of the POPL 20 model that only enforces the ordering rather than the flushing into the memory. And on this example, they both achieve the purpose. So are the two equivalent? So we formulate a theorem and prove that they are. For every program P, if you execute it under the PTSOSYN model, you will reach the same states as under the POPL 20 model. And this statement, it includes the program state and the non-volatile memory. So when programs crash and start executing their recovery code, they will start from the same non-volatile memory states. And that enables using the two models interchangeably. So while we prove properties about the recovery code, we can use either POPL 20 model or PTSOSYN model. And just to give you some ideas about how the proof goes, it is technical, but there is a main idea that the two models execute instructions differently. PTSOSYN persists writes eagerly, whereas the POPL 20 model doesn't actually need to persist them necessarily. So if the same states are going to be reachable, they are going to be reachable with potentially different traces. And the key insight there is that when a crash happens, then transitions that precede this crash, they only matter if they belong to instructions that persisted. If those instructions didn't persist, then you can reorder transitions however you wish, and maybe even remove them if that's what reaching the goal requires. So with this theorem proven, we have the POPL 20 model equivalent to the PTSOSYN model, and we can proceed to exploring sequential consistency. Of course, the base question is, what does it even mean to have this persistency with an illusion of sequential consistency? Which formal model does it correspond to? How do we write this down? Well, there are several things that several boxes that we might want to check. The basic guarantee that we want is that for single-threaded programs, TSO and sequential consistency need to be equivalent. In fact, maybe we would go on further and say that intuitively restricting TSO and removing the parts that make it weakly consistent should result in a C. So removing store buffers, for instance. Well, that is something that wouldn't work with the POPL 20 model, because it does need store buffers even for single-threaded programs to explain how persistency works there. But it would work for PTSOSYN, which is why we choose it for exploring these questions. And there are several extra guarantees that we want. So we want to ensure that data race-free programs have DSC semantics, and we want a compilation scheme that would enforce SC. So we start with PTSOSYN and simply remove the store buffers from this model. And the resulting model is actually quite simple. It has very simple looking transitions, which I encourage you to look up in the paper. And we think that this simple model captures implicit assumptions made in many papers of the prior work. So we prove that this version of persistent sequential consistency is connected to PTSOSYN with a data race freedom theorem. We prove that every data race free program P, when you execute it under the PTSOSYN semantics, reaches the same states as when you execute it under the PSC semantics. And importantly for such a theorem, DRF is checked assuming the stronger semantics. So you check it about the program P under the semantics of persistent sequential consistency. Important because it is simpler to check, of course. It is also important to mention that the notion of data race freedom here is not standard, it is extended. So let's see how. The conventional notion of data race freedom is more or less like this. Whenever you have two threads that can perform a write and a read to the same location, that is a data race. So if we take a look at this classic store buffering example, here on the left-hand side we have a write to X followed up with the read from Y. And on the right-hand side, we have a read from Y followed up by a read from X. Now, of course, these two threads can execute a read and a write to X at the same time. So there is a data race here. And in consistency models, if you execute this program under TSO, it will have behaviors that cannot be explained under sequential consistency. So for a data race freedom theorem, we would rule out such a program because it has a data race. And in that way, we would get an SC semantics. So we have a similar approach for the persistency. We consider this example where after a write to x, we perform a flush to y, and then on the right-hand side, after a write to y, we perform a flush to x. And then a crash happens. Under persistent sequential consistency, it cannot be that after the crash, we lose both a write to x and the write to y. If we consider all possible interleavings of these four instructions, it just won't be possible for both of the writes to get lost. And actually, under PTSOSYN, that's also the case. So it's not possible to lose both writes. But that's only with the CO flush. Or we consider more, if we consider trickier persist instructions that I haven't told you about yet, then strange behaviors can occur. So if we replace CO flush in this example with a combination of two instructions, CO flush opt followed up by a store fence, then the intention of what's happening in the example is the same. So you flush the write to y and the write to x. But now under PTSOSYN, it is possible to violate this idea that you cannot lose both writes. So we need to identify what is the problematic pattern here and rule it out as a data race. So for this reason, we say that in addition to conventional data races, we will care about situations when two threads can perform a write and a CO flush opt to the same location. So if we rule out programs with such data races, then that will help to push through the data race freedom theorem. Now onto the compilation scheme from PSC to PTSOSYN. The compilation scheme also extends the standard mapping of sequential consistency to TSO, where the idea would be to insert a memory fence between writes and reads to different locations. So for instance, if we take a look at that store buffering example, we would insert an mfence instruction between the write to x and the read from y in one thread and the same thing in the other thread. And then this way, we would conservatively take care of data races. So the compilation scheme that we propose for PSC to PTSOSYN is similar in that we take this example of writes and flushes, and we conservatively insert as fence between writes and CO flush opt instructions to different locations. So in the example from before, I would take the write to x and CO flush opt to y, and I would put a store fence between these two instructions. Interestingly, this pattern of having a write followed up by a flush of a different location is not very natural. You would typically expect writes to be followed up with flushes to the same location. So it is possible that this extra work that our mapping from PSC to PTSOSYN adds on top of the standard mapping has not a significant overhead, which is something that could be interesting to explore. In the paper, we prove the DRF theorem and the equivalence theorem using declarative models for PTSOSYN and PSC. These declarative models are simpler in formalisms than others that we saw, and we think that they might be useful for verification purposes. We also have an equivalent finite model for persistent sequential consistency. So if you fix the number of threads and memory locations, then the resulting model will be a finite state machine, which is simpler for formal verification questions and decidability. Overall, I've told you about the progress that we did in answering question relating the prior work with implicit and possibly informal assumptions about this eager and more synchronous behavior of persist instructions and the POPL 20 semantics. There is no need to revisit the prior work, and we answer that by proposing our model for x86 PTSOSYN with this eager and synchronous flushing, and we prove that this model is equivalent to the POPL 20 model. And we also explore how to provide an illusion of sequential consistency under persistency models for x86, which we do by formalizing what persistent sequential consistency means with the help of our PTSOSYN model, just without store buffers, and by proving a DRF theorem and by suggesting a compilation scheme from PSC to PTSOSYN. Thank you very much for your attention. And if you have any questions, please come to the session or ask them over email. Thank you.